Okay, back with more step-by-step. Numbers 26 and 27. See what we've got here. More derivatives and second derivatives, methinks. So let f be a twice differentiable function. That just means if you take both derivatives, you don't get any sharp corners. So that just means we can do anything we want with derivatives, basically. Don't need to get thrown off by that. Defined on the interval from -0.5 to 4.5. So what you see is what you get. And f of 2 is -3. Okay, might need that point later. The graph of f prime is shown here. So again, we're looking at a graph of a derivative, not the original function. And that graph crosses at 1 and 4. That's what it looks like here. And it's got a horizontal tangent line at 3, which actually doesn't quite look like that, does it? All right, and let g be the function e to the negative whatever the f function is. All right, so first step, write an equation for the tangent line to the graph of g, this function, at x equals 2. Well, let's see. Can we find the point? That means I need to know what the point is. The point 2 comma something. The point 2 comma g of 2. What's g of 2? That would be e to the negative f of 2. And f of 2 is -3. So that would be, the two negatives cancel out. That would be e cubed. So that's our point. And now I need to slope. Since I've got a little room here, I'm just going to go ahead and find the derivative of the g function here. G prime of x would be equal to, well, let's see, the derivative of e to the whatever is e to the whatever times, chain rule, times the derivative of what's inside, the derivative of negative f prime of x, of negative f of x, excuse me, is negative f prime of x. Right? So that's the derivative of the g function. So let's see if we can find our slope for our line. That would be g prime of 2. That would be e to the negative f of 2 times negative f prime of 2. And we did this already. That's e cubed times, what's f prime of 2? Well, this is the graph of f prime, right? This is the graph of f prime, and it looks like f prime of 2 is -1. So that's negative 1, that's just 1, and my slope is also e cubed. So turned out the point was 2 comma e cubed, and the slope was also e cubed. So that would be y minus e cubed is equal to e cubed times x minus 2. Funny looking line, but a line all the same. Okay. Find all values of x at which g has a local maximum. All right, here's the g function. So we find local maximums and minimums by trying to find critical points, right, where the derivative is 0. And I already found that derivative, so let's go ahead and set that equal to 0. Well, e to some power, this right here is always positive. So if I want this expression to be 0, it's not going to happen because of this. This can never be 0. I need this to be equal to 0. So let's see. The negative f prime of 0 is equal to 0 in the same places where f prime of 0, or f prime of x is 0. So looking up here, where are the zeros? 1 and 4. So this whole thing is equal to 0 when this part's equal to 0, which is at x equals 1 and 4. So I'll set up my number line and test some points. So I could test like 0 here, for example. I know this is always positive, so I don't even really have to look at this part of it, right? It's always positive. E to anything, positive something. So this is what I need to really look at. If I plugged in 0, then f prime of 0 is positive, but negative sign in front would flip it down, would make it negative. So got negative here. Try something in between here and here, like 2. That's negative 1, but the negative sign in here would flip it, make it positive. And then try something like past 4 up here. It looks like it's positive here, but it gets flipped by that negative sign. So looks like I've got decreasing, increasing, decreasing. So the maximum would happen here when I went from increasing to decreasing. Maximum at x equals 4. Because the derivative, g prime of x, remember that's the derivative of g, goes from positive to negative. All right. Find the average rate of change of g prime, the derivative of g, on the interval from 2 to 4. Anytime you see average rate of change, that means not a derivative, but an actual slope. So the average rate of change of g prime from 2 to 4 is simply the slope between those 2 points. So that'd be g prime of 4 minus g prime of 2. That's like y2 minus y1 over x2 minus x1, right? It's the actual slope, average rate of change. Now let's see what we can do with that. G prime of 4, that's e to the negative f of 4. Remember, this is my derivative. Oops, I'm pointing at something you can't see, right? That's my derivative. I have it written down here again, so I'll just point at this version of it. Times negative f prime of 4 minus e to the negative f of 2 times negative f prime of 2 over 4 minus 2, which is 2. Well, if you're looking at this thinking we might be in trouble here because we don't know what f of 4 is. We don't have any picture of the original function or any information there. It turns out to be okay, though, because, look, what's f prime of 4? F prime of 4 is 0. So since this term right here is 0, times, it doesn't matter what this one is. This times that is 0. Minus e to the negative f of 2. Well, let's see. F of 2 is negative 3. Ooh, right, that was given here. F of 2 is negative 3. So negative, that's our e cubed again. Right, we saw that show up up here in this problem. Times, sorry, my 2 is infringing on this space here. Times, let's see, f prime of 2, looking at the graph, f prime of 2 is negative 1, negative that, so that's positive 1 all over 2, so it looks like it's negative e cubed over 2. Right, that was fun. Now, if you thought that was messy, the second derivative of g is given by this. Now, we could find that, right? We found the first derivative. We'd just have to do the product rule on this, and we should get this. But they do this sometimes on the AP test too. They give you something like this because they don't want us to drop the ball finding this, so they sometimes give us some messy expression like that. All right, they want us to know, to determine whether g is concave up or concave down at x equals 1? Well, that's just a matter of figuring out if this is positive or negative, so that's messy, but you should be able to do that. That's negative e and negative f of 1, and then we've got f double prime 1 minus f prime of 1 squared. Okay, and all we care about is whether this is positive or negative. So, let me remind you again that even though we don't know what f of 1 is, e to the any power whatsoever, this is positive. There's a negative sign in front. So far I've got a negative sign times a positive sign. Okay, you with me? Because e to any power, that's always positive. Okay, now f double prime of 1. Look at the graph. This is the graph of the derivative, so if you want to know what the second derivative is, that's the slopes of this. So f double prime of 1 is the slope of this, which is clearly negative. Okay, so this is some negative number here. Subtract, and then what's f prime of 1? This is the graph of f prime. F prime of 1 is 0. So this term right here is 0. So I have a negative times a positive times a negative. That's positive. So G is concave up at x equals 1. And I think that's our, what more justification could you ask for? I guess you could say because g double prime of 1 is positive. It's greater than 0. Right? That's what concave up means. Alright, that was fun. And the last one. Let's see, again, we've got the graph of a derivative here. Defined from -2 to 8. It's got horizontal tangents at 1 and 5. And it's twice differentiable. That just means no funny business. We're all clear for finding second derivatives. And f of 3, the original function, is -2. Alright, so what's the x-coordinate of the points of inflection of the graph of f? And we talked about this before. Since this is the first derivative, the second derivative is the slope of this. These are negative slopes to positive slopes to negative slopes. So where those slopes change direction, in other words here and here, those are the points of inflection. At x equals 1 and x equals 5, the slope of f prime changes sign. If you're looking at the derivative, your maximums and minimums are your inflection points. I guess you could memorize that fact, but it's pretty easy to convince yourself, right? The second derivative is the slopes of the derivative. Here the slopes are negative and then positive, so that's where it changes sign, right? And that's the definition of an inflection point. Okay. For what values of x does f attain its absolute maximum value on the closed interval from -2 to 8? And show the analysis that leads to your answer. Well, let's see. What's going on with this f function? The original function, since these are the derivatives and they're positive all the way from here to here, that's a whole lot of increasing, right? Positive derivatives, positive derivatives. So all from here to here, the original f function is increasing, right? Increasing, increasing, all positive derivatives. And then for this little bit here, it's decreasing. So I think that it's pretty easy to convince yourself that since there's all this increasing and then just a little bit of decreasing, this is going to be the absolute maximum value of the function. So maximum happens at x equals 6 because f is increasing on the interval from -2 all the way to 6, and only decreasing on that little interval from 6 to 8. Okay. Using the known points given on the graph of f prime, for what values of x does the graph of y equals x squared plus f of x have a horizontal tangent? Well, horizontal tangent means derivative is excuse me, derivative is 0. So let's find the derivative of this. The derivative is 2x plus f prime of x, and I'm going to set that equal to 0. So what does this mean? It means we're looking for values where f prime, I'm going to tweak that equation around a little bit and say that f prime of x is equal to -2 times x. Well, here's our f prime values. Are there any values where the value of f prime of x, in other words, the y coordinates here, are equal to -2 times the x coordinate? And there's one. This one, right? At this point right here, f prime is 4, right, at -2. And then plug the -2 in here, -2 times 2, that gives that's the condition that we need here to make this equal to 0. So, for what, and you can check the rest, none of the rest of them work. So it happens at x equals -2. And give a reason for your answer. Well, because it works. Because 2 times -2 plus f prime plus 4, right? That's f prime of -2 is 0, right? Because it works. I guess that's my one small complaint about these problems is sometimes he asks for a reason where I think the AP test wouldn't. I think your work justifies that response there. All right, last part. Let g be a function defined as g of x is equal to x squared. That's a product for those of you who like to just toss your derivative rules to the side of the road into a ditch as you're taking derivatives. You must use the product rule on this. Find an equation for the tangent line to the graph of this at x equals 3. So I need a point and I need slope. So let's see if we can find our point first. G of 3 would be equal to 3 squared times f of 3. And if you remember way back when, they told us f of 3 is equal to -2. So that's 9 times -2, which is -18. So there's our y coordinate. Now we need slope. So let's see. G prime of x is equal to the derivative of the first times the second plus the first times the derivative of the second. And we can plug 3 into that now. Let's see what happens. 2 times 3 times f of 3 plus 3 squared times f prime of 3. Let's see. F of 3 is negative 2. We just did that up above. So that's, let's see, 2 times 3 is 6 times negative 2 is negative 12 plus, let's see, this is 9. What's f prime of 3? Well, here's the graph of f prime. F prime of 3 is 1. That's one of the points we got there. So that's 9 times 1. That's negative 3. That's our slope. And then we can write the equation for our line. How's about that? All right.